So as I've already told, in three-dimensional arrangement of the particles in the close-packed structures, there are two types of arrangement, that is square close-packed layers as well as hexagonal close-packed layers. In the two-dimensional arrangement, I have explained how in the hexagonal close-packed layers, how the layers are arranged in the form of AB arrangement. So now, let us see how the arrangement takes place in case of hexagonal close-packed layer, in case of three-dimensional arrangement. So first, whichever I have written in white, in the white font, you can see in this diagram. So here, this is the arrangement in whatever I have written in white chalk. So that is the arrangement in case of hexagonal two-dimensional layers. That is the first layer and the second. The second layer is arranged in such a way that each particle of the second layer is placed between the two particles of the upper layer. So we have AB type of arrangement in the two-dimensional structure. So whatever I have drawn in white chalk, that is the hexagonal two-dimensional arrangement. Now, as I have already told, in three-dimensional arrangement, there are extra layers which are placed over the two-dimensional structures. So now, whatever I have written in the other color, that is in brown, so you can have this arrangement, that is the next layer can be placed in such a way that the layers are placed in between the gaps of the first two layers. Now if you are considering these two layers, the upper first layer is placed in such a way that between the gaps of the first two layers, the upper particles are placed. So now, as along with that, the other layers are also placed so that the gaps of the lower layers are filled, or upon the gaps of the lower layers, the other particles are placed. So now you can see there are two types of gaps. So in chemistry, in solid state chemistry, these gaps are called as voids. Okay, so gaps are referred to as voids. So you can see here there are different types of voids that are formed because of the arrangement of the upper layer over the two-dimensional structure. So you can see here, this is the lower layer which I have written in white. So that arrangement of the lower layer is called as A, arrangement A. Now the upper layer which I have written in brown, so that arrangement, it is different from that of the arrangement of the lower layer. So that I have, let me write it as B. So the lower arrangement is A, the upper one is B. So now you can see here, just concentrate on the lower layer A and the upper layer B. So you can see here in the lower layer, there is one void here or one gap here upon which the upper layer particle is placed. You can see upon this gap, this particle, the brown particle is placed. So this gap is how it looks is, below there is a triangle because this is a gap which is triangle in nature, and upon this gap is covered by the upper particle. So upon the triangle there is one more particle. So if you join these 3 points of the triangle, that is of the void, to the upper particle of the second layer, you get a tetrahedron. So when you are joining, you get, see there are, why do you call it as a tetrahedron? Because 1, 2, the front surface and the lower surface. There are 4 faces. So that's why you get a tetrahedral structure when you join the void and the upper sphere of the second layer. So such type of void is called as tetrahedral voids. Okay, so tetrahedral voids are formed when the upper layer is placed exactly on the gap, exactly on the void of the lower layer. You can see one more type of gap is there. See here. Here there is already a gap in the lower layer. Again, the upper layer also forms the continuation of this gap. The gap of the lower layer is not covered by the particle of the upper layer. This gap is continuous. Even from the upper layer to the lower layer, the gap is continuous. So now, this type of gap has a triangle above. You can see here. Let me just show it in detail. See, there is a triangle here above, and below there is an inverted triangle because below there is one more gap which is inverted. So you can see here upper triangle and below there is a inverted triangle, when you join all the vertices of these two different triangles, you get an octahedron. You get an octahedron. So such type of voids, the voids are continuous from the lower to the upper layer, that is called as octahedral void, or they are called as octahedral gaps or octahedral voids. Okay, so these are the two types of voids that are formed when the second layer is placed over the first layer of the hexagonal closed packed structures. Now, as I have already told, in three-dimensional structure, how the arrangement takes place. Suppose if this is the first layer, second layer, third, fourth, fifth, and so on. We were just speaking about the two layers now, the lower layer and the next layer. Again, there will be so many other layers that are placed above these layers. So now, for the placing of the next layers, there can be again two possibilities. The one possibility is, here you can see the two possibilities are, first possibility is covering the tetrahedral voids. The next possibility is covering the octahedral voids. Now, this is the second layer. Let me just show it to you. So, this is the second layer. Let me just highlight it. So, here you can see these are the octahedral voids, which is continuous from the lower layers. Okay, so these are the octahedral voids. Now, if I am just drawing one more layer of the second layer itself, we get it like this. Okay, so these are nothing but the octahedral voids, and here we have even the tetrahedral voids of the second layer. So there are two different types of voids that are formed by the second layer. So if you observe this void, just if you observe this void, this gap is not continuous with the lower layer. That is, this gap has one atom of the lower layer. So that's why this void is the tetrahedral void of the second layer. So now there are two types of arrangement of the third layer. So how you can arrange? First arrangement is placing an atom above the tetrahedral void of the second layer. If I place an atom over the tetrahedral void, so this is the tetrahedral void. If I place the third layer above this tetrahedral void, that is, if I place it here, the third layer, you can see that the third layer is exactly having the arrangement of the bottom layer or the first layer. So here, this type of arrangement where the tetrahedral voids of the second layer is covered by the third layer and the arrangement is exactly same as that of the first layer, this type of arrangement is called as AB arrangement, and it is having a specific name called as hexagonal close packing or HCP arrangement. So this arrangement is shown by magnesium, zinc. These are the metals which will crystallize in HCP arrangement. Next arrangement is how we are going to close the octahedral voids. So octahedral voids, you know that here, this is the octahedral void. We have one more octahedral void here. These are the different octahedral voids which are continuous from the below and the upper layer. There is a continuous void from the upper to the lower layer. Now if I have to cover this octahedral void and place the third layer. So this is the octahedral void. So third layer has to be placed like this, so that the octahedral void is covered. So now if you consider here, this layer is not having the arrangement of the second layer nor the first layer. It is completely different. Such type of arrangement is called as ABC type of arrangement. This is ABC type of arrangement, whereas the first one was ABA type of arrangement. When the ABC type of arrangement takes place, it is called as face-centered cubic arrangement, FCC, face-centered cubic arrangement, and example for metals crystallizing in this arrangement are copper and silver. So this is about how the different types of voids are formed, how we are going to arrange the different layers in three-dimensional structure, and how the arrangement will be similar when you are closing the tetrahedral voids or when you are closing the octahedral voids. You can also see here, if you observe the number of atoms, if the number of atoms or number of particles that are forming the solid are n, okay, the number of tetrahedral voids, you can see here, for each octahedral void, okay, if this is the octahedral void, there are 2 tetrahedral voids. Okay, so for each atom there are 2 tetrahedral voids. There is double number of tetrahedral voids and equal number of octahedral voids. So I can say octahedral voids will be n in number if the number of atoms or number of particles are n. So number of tetrahedral voids will be double of that of the number of octahedral voids, because for each octahedral void you will have alternatively 2 tetrahedral voids, as you can see in the picture. Okay, so this is about voids and how to calculate the number of voids and how do you arrange the different layers one above the other. Next, coming on to calculation of density of a unit cell. So usually this will be asked in numerical part of the questions, where one of these will be given as the unknown and you have to calculate the other, that particular value using the known values of the other units. Okay, so now you can see density is given by rho, which is given by Z m divided by n naught into a cube, where Z is number of atoms per unit cells. So how to calculate the number of atoms per unit cell, I have explained in my previous video. If you have not watched the video, you can watch it. I have given a detailed explanation about how to calculate this number of atoms per unit cell for the different unit cells such as space-centered cube, the body-centered cube, etc. I have given the link for the same video in the description box. So next, m is nothing but molecular weight of that particular particle. So n naught is nothing but the Avogadro number, and a is the side length, unit length of the particular unit cell, the side length of the unit cell. So that will be given. Any one of them will be given as the unknown. Using this formula, you are going to calculate the unknown. You can also use one more formula, that is Zn divided by n naught into V, where V is nothing but the volume of the unit cell. So this is how we are going to calculate the density of the unit cell by this formula. So in this video I have explained how the arrangement of particles are taking place and how the closed packed structures are arranged in the solids, and also I have explained how to calculate the density of the unit cell. I thank you all for watching the video.